Revenge of the Rahul, take 65.
Action.
Action.
All right, so today I'm going to be giving a talk about the CLA, and the intended audience is for new employees who are trying to learn about the CLA, a little bit about concepts, but a lot of that is documented in our white paper. So a lot of it is kind of the practical CLA that we have now, what the different regions are, and kind of how that affects the data problems that we see. So with me again, I have Thomas and Louise, and they're going to be asking questions. So just to start off, as we described in our white paper, the fundamental units of in the CLA, which stands for Cortical Learning Algorithm, are our cells, and the cells are arranged in columns. So that's what I've drawn here, is that we have a whole bunch of cells, and they're arranged in columns. Fundamentally, the CLA has two functions. One is to make similar inputs, to give them a similar representation in the spatial pool, in the CLA. That's what we call the spatial pooling aspect of it. And the other aspect is to learn sequences of patterns, and that's what we call the temporal puller. So the way it works, and again this is described in our CLA white paper, is that, say this is our CLA with a certain number of columns and cells within these columns, and we have some input coming into the CLA, and the way we think about input is just as a binary vector, a vector of zeros and ones. So here is a sample input. The way we have our CLA arranged right now is that each column, and we're treating all columns as a single entity right now, each column is connected to some random subset of the input bits. And there's two notions here that, so it's each column can see some subset of the input bits.
Random?
Huh?
It's random?
Some random subset of 50% is the number we're using right now. So this is not, I haven't drawn out 50%, but it's randomly initialized. We call this subset the potential pool of the column. These are all the inputs that this column could potentially be activated by. Each connection here has what we call a synapse. This is just the connection between the column and the input. And each of these synapses has a value associated with it called the permanence. This permanence goes between 0 and 1. And basically, the basic thing here is when a synapse is below a certain threshold, when its permanence is below a certain threshold, it will not respond to that input bit. It will not be affected by the input bit. When it is above a certain permanence, it will be affected by the input bit. So that's the learning that happens on a column level, is that we adjust these permanence values. So, and I'll talk about that in a second, about how that learning happens for these columns.
Okay, so question now. The 011, 000, that is already the SDR, right? The representation.
It is a binary representation. It's not necessarily sparse. We don't enforce kind of, SDR stands for sparse distributed representation. Right. It's not necessarily sparse, but it is kind of some distributed representation. And later on I'll talk about how we take actual input records and get this representation.
Okay.
But for right now, just assume that we have this kind of binary input given.
Yeah. So these supposed to represent sort of one record of the raw data.
Right. So this represents one record of the raw data.
Okay.
The way we compute, so when a new record comes in, there are two processes that need to happen. This record comes in, first we have to select which columns become active. So in general, we have a large number of columns, but we only pick a small subset of them to become active. secondly, once we've selected which columns become active, we have to select which cells within those columns become active. The concept in the CLA is that the active columns are a representation of the current input. It's some way of representing what the current record was. In such a way, the idea is that we want to do that in such a way where similar inputs become similar representations in the spatial pool.
Question.
Mhm.
So number of columns, is it fixed size or?
Right now in what we have in implementation, everything is a fixed size. We have a pre-allocated number of columns and number of cells, and that doesn't grow with time.
Okay. And the question. So let me think. And the 2D aspect of it has no meaning.
No, there's no meaning to the 2D aspect.
Okay.
Here is just
It's
you
just
just
how you
columns,
present.
yeah, and then so I drew them vertically, and then cells within those columns. So it's a nesting.
Column. Columns means
I drew
the
them
vertical.
Yeah. This comes from neuroscience, where in the brain they're actually arranged in these like columnar formations, where they're stacked vertically. For us, it's just a conceptual distinction. I mean, they're not actually laid out in any space or any sort. Well, we have the notion of columns, and each column contains a certain number of cells.
So even cells within the same column, there's no meaning.
So there is a meaning. So first
Okay.
thing so that's what I was saying. There's a two-step procedure. First, with the input, we want to pick a certain number of columns that are active. That tries to make a representation of the current input, such that similar inputs get more shared columns. They look similar at the column level. Then, when we learn sequences, within, say, this column is active, different cells represent different temporal contexts, different histories. So, for instance, say we had an A, B, C, and an X, Y, C pattern. When C comes around, it would get the same columns activated because it's still C. So the input here, at this time step, the input is the same. So it should activate the same columns. However, it should activate different cells within those columns because this C is one that came from a B, whereas this C is one that came from a Y. So that's kind of the basic fundamentals of the CLA, is that columns represent the current input, and the cells within the column represent that input with a different set of history behind it. That was good. That's the most basic overview of the CLA. Now, to pick which columns are active, each column has a potential pool to the input. That is, there are certain input bits that it is looking at. But not all of these, it's not actually responding to all of these, the input bits it's looking at. We have this value called the permanence that we say is if it is above a certain threshold, that this is actually connected. I'll say this is connected. It means it's actually looking at this bit. Whereas if this is below a certain threshold, it is not connected.
So it's binary.
So it's binary. It's
not
not
like-
awaiting
it's not awaiting.
like traditional neural networks. It's a binary threshold of above or below. There's evidence in the neuroscience that the strength of the synapses is not necessarily, in fact, the strength of the activation, but it's how long this synapse sticks around input. So the learning rule we use for columns is that, so say I use this symbol, this arrow symbol for connected, meaning that the permanence is above our threshold, and this symbol is a line saying it's not connected. So let me just, for example purposes, change this to a 1. When a new input comes in, for each column, we compute its overlap score. We're saying how well does this column overlap with the input. By overlap, we mean how many of its connected synapses are 1s. So in this case, we're connected to that bit, but it's a 0. So we don't count it. Here, we're not connected to this bit, so even though it's a 1, we don't count the score. In this one, we do count its contribution because we're connected to it and it was a 1. So this column gets an overlap score of 1. Similar, we can go each one of these. So the set of all these bits that we're looking at, connected and unconnected, is called the potential pool. So right now we have we set it such that each column has a 50% potential pool. It's connected to 50% of the input bits randomly. Then the number of, but that doesn't mean it sees 50% of the input bits, but it doesn't mean it's connected to all 50 of them. That depends on the permanence values. So first thing we do is we compute the overlap score for all the columns. So say the second step is we have a score for all these columns, but we want to enforce sparsity because we are trying to get sparse distributed representations. So what we do is we take the top 2% of columns, the columns with the top 2% of activations here. So for illustration purposes, let me just make these both 0. So in this case, after we've computed the overlap for all the columns, we'll say we'll take the top 2%. In this case, let's just say we selected this one and this one. It's not drawn to scale, obviously. So now these are what we call our active columns. We've selected, so right now we're just ignoring the cells. We're just looking at the columns. We say these columns are now active, they're fired. And that is our spatial representation of the input. The idea is that similar input bits, right, will activate similar columns because the columns are looking at certain input bits. So certain input patterns that have similar bits will activate similar columns. In this example, you kind of don't see the purpose because there's about 6 bits active here. There's 4 columns, 5 columns here. It's about the same. But if you had an image, say, that had hundreds and hundreds of bits active, and you still were only having 40 columns active, it's a compression mechanism. It compresses the image or the input such that similar things get compressed to the similar values. So the kind of the opposite of a hash function, where a hash function tries to spread out similar values, right? Because it tries to spread them out over the space. So that's how we select our column representation of the input. Now, when we turn learning on in the columns, we want to adjust the columns such as they better match the input. So what we do is that we look at all the bits, we look at all the columns that are active, and we say, okay, for this column that was active, let me make my synapses better match my input. So for this one, I was connected, the input was a 1, so let me increment the permanence here. So the permanence was like 0.2 here, let me increment it to 0.3, which means I have a stronger, I'm reinforcing this connection. But again, it's still a binary thing, above or below threshold, but we're still saying making this connection more permanent. For this one, it was below, it was also active, so say this was 0, that was the permanence before. Now I'm going to increase this to 0.1, because the type of patterns that activate this column tend to have this bit more. This one, I was expecting something here because I was connected, but there wasn't actually anything here. So I'm going to go from 0.2, I'm going to go down by 0.1. And these increments and decrements are actually parameters. And actually, the decrement is actually something we swarm over. Is how much we decrement. Right now we have a fixed increment of 0.1, but it's really the ratio of the increment and decrement that matters. So you only have to swarm over one of them and keep one of them constant. So this is basically how we learn columns. Is that we compute an overlap score given our connectedness right now. For the winning columns, the ones that were selected, so for these columns that were not selected, they weren't in the top 2%, we don't do anything to their permanences. But for the ones that won, we try to make their inputs better match, make their synapses better match the inputs. And this is how we achieve that compression that similar inputs get similar columns.
Reason why top 2%?
2% itself isn't necessarily
Sparse.
it's sparsity, yeah. So that's the ratio of sparsity that we want. I think 2% also came from some neuroscience research, like is in the ballpark of what we see in the brain. But
So that's
yeah,
there's another side.
yeah. But the basic point is that we want sparse representations. So any questions about the columns right now?
Question about, you mentioned about those you didn't select, you won't
No.
adjust. So why is that? What do you give up, or what's the give and take like that?
Right. So the reason we don't adjust these is that they're responding to other patterns. So just because that pattern didn't occur right now, like maybe this is a pattern for an A, right? The other ones are a pattern for a B. Just because a B didn't occur doesn't mean you want to forget about B. You don't want everything to learn A's, right? You want to have some columns that know about A, some columns that respond to B, some that respond to C. Here, say it was connected and it was a 0. The way I've drawn out A, B, C here, it's like they're very clean inputs. But, you know, say there's some noise, you know. That means there's an A, but sometimes this bit is on, sometimes it's off. So you want to kind of adjust your representation of A to be closer to what you see in the world, but you don't want to penalize the other columns that are tuned to different patterns.
I see.
Okay. So, in general, this is what we call the spatial pooling aspect of the CLA, the part that makes similar spatial patterns, meaning instantaneous and time, look similar, pools their representations together. Now you asked about the cells within the columns. That's how we learn sequences. So in general, kind of in the steady state, what we have is that we'll have one or a few cells in each column be active. So before we were talking about selecting which columns are active, but there's a separate process after that to select which cells within the column are active. So right now we've just selected the active columns. Say from the previous time step, this column, this cell, and this cell were active. When in the CLA, when certain cells are active, well, we have 3 different states. We have inactive, which means nothing's happening. We have active, which means that they were selected by the current input. And we have predicted. We have a 3rd state called the predicted state, which means that this is what we expect to see happen next time step. So hypothetically, say we have these 2 cells active in the current time step. They may be predicting that this cell and this cell are going to fire in the next time step because of the history. And we can talk about how they learned those in the first place. But these cells have learned to be active, and they learn to transition to what they expect to happen in the future. Now, in the current time step, when we see that input, and this column and this column become active, what we do is that we say, in this column, were there any predicted cells? Like, was I expecting to see any a certain cell here? If so, then activate that cell within the column. So I've activated this column.
So enforce it.
Yeah, but I enforce that this is the cell.
It's a good prediction.
Yeah. What this means is that, say these 2 columns are the ones responding that were B, they relate to B, and these 2 ones are for C, and we expect we're learning the pattern ABC. So say these were B and these were C. That means that these cells are the cells that say, hey, I saw C right now, but I saw C that followed from a B. So what we'd have to next time, when B fired, say we saw those cells, they were predicting these cells, and then when we saw C, we'd see that these cells are active, and now the B cells are no longer active. Does that make sense? How the cells represent the context?
So the prediction representation is it's another state.
It's another state. There's 3 states for the cells: inactive, active, and now say this column represented Y, and that was what we saw last time set because we're saying X, Y, C now. They might be predicting different. They're going to be predicting different cells in the C columns because they're going to say I still predict a C next. But instead of this one and this one, as I was before, I'm going to be predicting this one and this one, say. Now, when you see a Y, so you have this cell active, it says I'm a Y, and I'm predicting C, but I'm predicting that C and that C. So they're 2 different representations of C. Now, when these C columns become active, we select the ones that were predicted. So we say, oh, my cellular representation is this and this. So I have 2 different sets of cells active for C, even though they're both C's, but they're now C's that came from different places. So they get different cells activated. And that's the basics of how we learn sequences. Now, say,
So just one question.
yeah.
So it means that in every iteration of the algorithm, those states are, these are a new set of states, really, right? I mean, that applies throughout the temporal puller.
Yeah, in every iteration there's a new set of states.
A new set, okay.
Mhm.
Yeah, the states really are reset.
Now, what happens, say, if some column gets active that you didn't predict? For instance, say I actually saw A, B, D occur, right? And I wasn't expecting that. So, sorry, these are the 2 that I've learned. Say I actually saw A, B, and then D. And say, for instance, this column was representing D's. I should have drawn more columns, but so what I was predicting as before, I was predicting that after a B, this cell and this cell are in the predicted state, right? Because B is active, and from B comes C, and these specific C's become active. Then but if I see a D, meaning that the input pattern activated this column through the way through picking the best overlap score, which cell do I pick now? I have nothing predicted. You turn on all of them. All of them. Because we say we don't know which context we're in anymore. We don't know what history we came from here because it was so unpredicted. So this, right now, the term for this activity is called bursting.
So it's a new sequence?
Right, so inference-wise, we say we don't know where we came from. We just know it was a D. And then we have to learn a new transition now. So we actually learn a transition from B cell. We pick one of the D cells, and we say, okay, from now, next time I see it, I'm going to learn that B to D is this cell. We learn a new context for D. But the first time we see it, we burst. So initially, before you've learned ABC, you'll just keep bursting, and you kind of then form these connections. And there are details about, how do we learn this transition? How many times do you have to repeatedly see it until you've actually learned it? I'm not going to go into all those details, but this is the high-level concept of what happens when we learn sequences. is that we learn these transitions, and we're trying to figure out which cell within a column is active. Any questions about that? That in terms of conceptual parts of the CLA, this is about all I'm going to go into. Then I'm going to talk about a little bit more about the current implementation of the CLA and kind of how do we get these input representations, how do we use it to make predictions, how do we do multi-step predictions, things like that.
So the bursting really applies at the beginning also, right? I mean, it's
Yeah.
when you first start from scratch, it's the same principle applies, really.
Right. When you first start from scratch, everything is bursting, you know, because you haven't learned any transitions yet. Also, the way anomaly detection works, I can speak to that since we're here, is what we basically do is we say, of the columns that were active, how many were unpredicted, which is essentially saying how many are bursting. Yeah. So in this case, say, you know, this one was bursting, but this one was actually active too, and this is shared between C and D, and this one became active, right? So we can say 1 out of 2, yeah, this is bursting, this is not bursting, so 1 out of 2 were unpredicted,
And that's the score.
and so the score is 1/2. So that's how the anomaly score works. The thing is, because the CLA it can actually have multiple columns in the predicted state at once. You can have, you know, here I have 2 columns representing state. You could have 4 columns being predicted. So you can represent multiple possible predictions. So that's kind of that versus just doing prediction accuracy. It'll let you.
So how much of this is dependent on the binary representation?
Sorry.
The binary representation.
The input representation. It depends on the form of the binary representation. For instance, for numbers, you can't just feed in kind of the 8-bit or a 16-bit because it needs the property that is distributed. What that means is that a change in 1 bit is equal no matter which bit you change. If you actually do like a real binary representation of a number, like an 8-bit representation, the problem is if you change this bit on and off, that has a bigger impact on the value than this bit.
Right.
So you can't just do the overlap score like we did before because you have to weight them somehow. So we do something conversion for numbers and for categories to get new binary representations in there, and I'll talk about that later. That's what we call the encoders. So it needs that property at least. Beyond that, you just kind of want the general property that similar things have similar bits by whatever you measure similarity by. In images, this happens naturally, right? Because if you just had a bitwise image, 2 images that are visually similar will have similar bits.
Right, but something that has
Something like numbers, you have to.
most significant bits and stuff.
Yeah,
That's
something
not-
with most significant bit and least significant bit won't have that property. So you have to pick some other way of doing it. That's a good question. Okay. So I'm going to keep this up here, but now I'm going to start talking about how we actually have these in the code. And kind of, this is a very clean theoretical conceptual view. Talk about more of the practical implementation and how we all this. So in our code base right now, we have a class called the CLA model. And the CLA model is composed of multiple regions, and there's actually 4 of them right now. So the CLA model looks like this. We have the sensor region, the spatial pooler, temporal pooler, and the CLA classifier. And I'm going to walk you through what the data flow is in between each one of these layers and how we use these to produce predictions. And anomaly, I can talk about how we use it to produce anomaly scores, but the anomaly score is actually easier than the predictions. So the sensor region is this region that converts whatever the input record is into that binary representation. So the input to this region is actually a dictionary that says, I'm going to use the example of power consumption in a building. So it'll say the consumption, 1500 watts, say, and the temperature, 15 degrees, and say for some reason the building's color matters. So it does. So it's a white building.
Yeah.
So this is just a straight up Python dictionary that goes into this sensor region. Now what comes out of this sensor region, and I'll actually explain this near the end, but is this binary vector that represents this input somehow. That's what I was drawing down here. It's this that is connected to our columns. So that is what this is. This is of a variable size. As in, there are certain parameters of the sensor region that affect how many bits are in this vector. And I'll explain those too when I talk about how we do this conversion. But that's actually one of the set of things we swarm over is the size of this. Then we go to the spatial pooler. The spatial pooler is, so in our code base, or in the CLA model, we make we have just in the code for modularity separated out the tasks of picking active columns versus picking active cells within the columns. So this initial learning task of picking which columns are active, we call that the spatial pooler. In code, we actually have a separate class for that called the spatial pooler. So that is just responsible for picking columns. It does not look at the sequences, it does not look at the cells within the columns. In some ways, it just treats this all as a single cell, like it treats each column as a single cell. Now, in our current CLA approach, we have a fixed size spatial pooler that is 2048 columns. So, and 2% of that is around 40, so we have 40 active columns. So the output of the spatial pooler is a binary vector that has 2048 entries and 40 of them equal 1. So, and that's perfectly mapping just the column applications here. Then we have the temporal puller, whose sole job is to take that input and just decide within each column which cell to pick, whether it's to burst all of them or to pick a single or a couple cells within the column. So that, right now, currently, in our implementation, we have 32 cells per column. So who can guess what the output vector of the TP, what size it is?
For it, 32 bits.
Sorry?
2000 is active columns.
Mhm. And the temporal puller is responsible for picking active cells, not active columns.
So it's 32
It's 32 per column, so it's actually 32 times 248, which is 65,000 and 5,036, I think. So yeah, so this is another binary vector that comes out, which is bigger, and it has and the size of this is 65,000. And it has a variable number of ones because some could be bursting. In general, if everything's perfectly predicted, it'll have around 40 because 40 is one per each column. But sometimes you can have multiple in each column. Sometimes you can be bursting. So it's a variable number of ones, but it's not very many. It's relatively sparse still. And then we feed that into the classifier. And the classifier is something that's non-biological that we added to make it easier to make multi-step predictions. And if you ever wondered why in our multi-step predictions, if you do 5 steps ahead, why don't you get 4 steps ahead and 3 steps ahead and 2 steps ahead and 1 step ahead? That will now be explained. So the CLA classifier is something we devised to take this state, which has a certain number of active cells, and to produce a prediction from it. And the way we do that is to actually, at each cell, keep a lookup table. And at this lookup table, say we're predicting colors. In each cell, we're going to keep a little lookup table that says, each time I saw red, or how often when I was active was it red? I'm going to, that was 20% of the time. How often was it blue? 60% of the time. Like that. So every time I'm active, what was the value of the what was the value of the predicted field? I'm going to keep a little histogram basically. And then to produce the prediction, we just for all the active cells, for everything that was 1 coming into me, I'm gonna add up all these histograms, and I'm gonna say in total what is the most likely value, and I can also give probabilities on the other values as well. The way I drew this is a little simplistic for a number of reasons. One, you're trying to make predictions ahead, right? You don't want to so you don't want to keep a lookup table of the current value. You want to keep a lookup table of the future value. So what we do this sliding buffer. So if you're trying to make a prediction for 2 steps ahead, for instance, if the value was white, this was the sequence we saw. We're gonna save this binary vector. When we see white, we're gonna save that as some state. And then when we see this, we're trying to make a 2-step ahead prediction. So we want to associate this state with the color blue.
I have a question. When you went from the temporal to the CLA classifier, those 32 bits were 32 3-state bits.
No, we only pass in the active ones.
So not the predicted.
Yeah, that's a good question. So we use the predictive bit to select which cell should become active. But we don't actually use it to make predictions. We use it just to say which history am I in.
So what's expected?
Yeah, what's expected. And so when I do see, that expected thing, I know which cell in the column to pick instead of bursting. But the way we're doing it is we're classifying the active bits with the future value. So here, these are the active bits, and I want to associate that when I see white, blue comes 2 steps later. So these active bits should get associated with blue. So we keep a time delay window, a sliding buffer, where for each one of these we save what the active bits were. So we keep a sliding buffer here of the length of our prediction window. So in this case, it's 2. So we keep 3 steps here. And when we see blue, we're saying, okay, now we'll associate this with white. So we'll go back in this lookup table for white. For each one of these bits has a lookup table like this, and we'll increment the value for blue. We'll say that, oh, we see a blue again, so now it's more likely that when I saw white, blue will occur next. So the classifier works by keeping a lookup table for every cell of what a histogram of what the predicted value tends to be, whether that's multiple steps out or a single step out. This is why when you make a 10-step prediction, you only get a 10-step prediction ahead. You don't get the 9-step ahead prediction. You don't get an 8-step, because we're not playing the sequences forward in a predictive state. What we're doing is associating the current state at time t. We're making an association between that and what we see at time 10. So what happens if you want to do multiple steps? Really simple. We keep multiple lookup tables. You know, this is the 10-step table. We keep a 9-step table. Yeah.
Could you give a sense of the overall memory usage?
Yeah, the memory.
The classifier is the highest memory usage of the whole CLA, because if you have a temporal puller, there's 65,000 of these little lookup tables.
Steps.
Huh?
Times.
For times the number of steps. Yeah. So we have certain optimizations around here in the sense that we only store the values that we've seen at every bit. We don't store zeros and things like that. But it's still, I'd say it's over 50% of the memory usage of the system is in the classifier. Although Scott did a lot of work with the porting it to C++, which has reduced it significantly, because these lookup tables in Python, they can have a lot of overhead because they're very small objects, but the whole Python wrapping around it makes it bigger. Yeah. So, any questions about the classifier? Now I'm going to talk about how we deal with real values rather than categories.
Right, so that'll be my question.
Okay. So then the main question is, this is all fine and dandy for fixed categories that are already discrete, but what if you have a continuous value? For instance, consumption, the problem I actually started with. So we're going to go on a little digression first on how we get the binary inputs for those, and then we'll talk about, it'll be very clear what gets fed into here. So the main thing is, if you have a continuous value, we have to discretize it. So basically, the big question is, how big are the chunks, or how do you discretize it? So for every scalar value, we have to kind of know what the min value and max value is and what resolution we want to discretize it into. How many buckets do we want to chop that range into? So if we know the min and the max, we're going to operate under that assumption first. And we know the number of buckets is very simple. You just take the min and the max and chop into that many buckets. So how do we turn these things into binary representations? For categories, it's really easy. We pick some number of bits that we want to use to encode the category. In this case, I think it's 121 is our default. And we pick a certain number of bits that we want to turn on, that we want to be active for any category. In this case, it's 21 is what we're using as our default. And we very simply just say, pick 21 random out of this 121 and represent the color white with that. Pick a different 21 random and associate the color black with that. So you might get something like this is white.
So it's not necessarily sparse.
It's sparse just by the way we pick these numbers. We're kind of enforcing that this isn't very large compared to this. So this is what we talk about when we say we're encoding the category. It's converting it from that raw value into this binary representation. The number of bits total that we have is a parameter that we call n, for number of bits. The number of bits that we have active we call w, for width. And it'll be more apparent with scalars why we call this the width. These n and w parameters, we swarm over them, but what we fix w because it's the ratio that matters. So we fix w and we swarm over n. So this, when we run a swarm, this is, in addition to the field combinations, this is one of the things we're searching over is this value of n. For categories, actually, we don't search over that because it has less of an impact on the performance because you're just picking random bits anyway. What do we do for scalars? So for scalars, we do a representation like this. We pick n bits, and we say that there's a min value and a max value. If our input is equal to the min value, then we turn on the leftmost bits. This means in this case, and how many do we turn on? We turn on W of them. If it's a higher value, we represent it as this. If it's an even higher value, we represent it as this, just the next most over. So we always keep a contiguous block of active bits, and there's W of these, 21 in practice, and there's n total. Now the thing is, the size of n affects how, this has got a limited resolution, right? If this goes from 0 to 100, a difference of 0.1 is not going to show up here. So the value 0 and the value 0.1 will both get the same representation, because they're a very small difference. Because when you have a representation like this, the maximum things that you can represent here is n minus w plus 1. That's how many different states there are, how many ways you can slide this over. So the number of buckets you have then is max, or the size of each bucket is the max minus the min over n minus w plus 1. So this is why here, searching over different n's is very crucial. Because if you have an n of 500 here, like a very high n, then a range of 0 to 100 you can resolve up to like a 0.5. Versus if you have an n of 20 or 28, you can only resolve very big chunks, like everything within a range of 30 will look the same to the higher levels. So here we swarm over this value of n. And the range, it goes from 28 to 521, where the w is equal to 21 always. So this kind of gives you a sense of the range of resolutions that we search over for every field.
Is it fair to think about the n also as some means of noise reduction? So in other words, if you want to use small number of n's, it discretizes the input in a way that turns off some of the noise, right?
So one of the reasons we swarm over these different values of n is that the bucket size, you might think that, you just always want the highest bucket size because you get the maximum resolution. But the problem is, if you can have a lower resolution, you can kind of discretize the noise all into one bucket. Because you'll say all the noise kind of looks like one value. So yeah, if your noise is larger than your patterns, then you may also miss your patterns too. But at that point, it kind of comes down to the definition of what is noise and what is pattern, right? Because if your patterns are small and your noise is large, like what does that even mean? But yeah, so this is very crucial as a denoising technique too. It's part of why we search over it.
So question, when you say swarm between that two numbers, so you basically try everything? Or
We don't try everything. We use the particle swarm optimization technique that I talked about last time to do a guided search over that. Because say you have 3 fields, you've got 3 dimensions that you can search over, so they all interact, so you can't just try everything. You have to do a guided search of some form. Yeah. Is that clear? I'm sorry, guy.
Minute 20.
Okay. So now the question, we come back here, what do we keep in this lookup table, right? Because say the predicted field is a scalar, we learned how we binarized it, how we turned it into this representation. And by the way, that's why I said this has a variable size, because it depends on the size of the ends that we picked. But what do we put here? Because actually, in each one of these, we want to keep the actual value. We don't want to keep this kind of encoded value. So in the lookup table, we keep the bucket indices. So we can say this is bucket 1, bucket 2, say bucket 4. That means that, say, we index these different states. We could say that this was bucket 0, this representation that we gave, that's bucket 1, and so on and so forth. And this would be 1, 2, 3, 4, 5. This would be bucket 5. Okay, so we just went over how scalar values are encoded and what we mean by bucket indices. So we can give each one of these a bucket index, and in the classifiers now, we store, when this cell is active, which buckets do I tend to see? And we store a histogram of the buckets. Now if you notice, that breaks this kind of clean passing up model too, because now the classifier needs to know what bucket the input was, right? But that came through the sensor region. So in fact, the sensor region has, in the CLA model, a direct connection to the classifier to pass what the predicted value is, or the value of the predicted field. And for scalars, this is actually the bucket index. So the data flow is really like this. And I forgot to draw what comes out of the classifier. It's a prediction. So in this case, say you'll predict 1200 watts next. Now, if you notice, the prediction is not a bucket index, right? I said we're storing, for scalar values, we're storing what the bucket index is. And we're keeping a histogram of that, not of the actual value. So how do we get that value? The classifier also does one more thing if it's scalar values. Independently of the cells, it has one global table that says for bucket 0, it keeps a moving average of what value I tend to see here. So whenever I tend to see something like, so actually this will pass up the value as well as the bucket index from the sensor region. So in fact, what we pass up here is the value 1500, and we'll say it's bucket 4. We'll pass up both of those pieces of information. So we can construct this moving average table. So the classifier, these histograms, will produce which bucket we think is the most likely bucket, and then we'll use this table to translate those into actual scalar values. So each bucket gets one scalar value associated with it, but it's a moving average value, which is, in the past, by sometimes, we've gotten burned by the fact that if you have a very coarse encoding, very few buckets, that still looks like a good predictor because this moving average can kind of pick the slack. One last note I forgot to mention when we talk about scalar encoders is what happens if you don't know the min and max beforehand, right? There's a lot of cases where that's true. So is everyone good on the moving average part of it? That's just a little aside, but it's important to how the classifier works. But like I said, we have a min val and a max val. And given that and the number of bits on, we can say that any state like this represents a certain range. Then we use that by taking the min val and max val, dividing it by the number of states that we have. If we don't know min val and max val, we do something very simple and very trivial. And this is what we call our adaptive encoder. simply say that we start this off with a min of 0 and a max of 1. Now what if a new value comes in that's greater than the max? Very simple, we just change this. We just say, okay, now, say the new value that came in was, say, 55. We say, okay, now the maximum value of this range is 55. This causes a lot of issues, because now, this state, which used to represent 0.2, it now represents like 4 or 8. It's the same thing. And the other layers are not aware of this yet, so they have to relearn. So it kind of invalidates all the learning that's happened higher up, including at the classifier level, right? Because it had histograms over buckets.
All the histograms are moving average.
Huh?
All the histograms are
Yeah,
not valid.
right. Exactly. None of the histograms are valid. So what we do right now is that if we don't set a min and max, we kind of hope to God that these changes happen in the beginning. So that we kind of capture the range.
And
after
outliers,
that.
you
Huh?
and those outliers, you
If there are outliers, you have big problems, because, and we have seen this before. Say there's some the general range is between 0 and 100. There's some random outlier, it's just the data, it's a query issue. And the value goes to like 65,000 or something. Now what can happen, and this was just a single spike for some reason. Now what will happen is that 0 to 100 all resides in that lower bucket, in this state right here. So
tend to move an average.
So from the CLA's perspective, it actually is a very easy prediction problem now, because all we have to predict is this state over and over again, right? They'll have the same columns, so we can just predict that those columns keep happening, right? And the problem is, and because we're using a moving average to make a prediction, it may even look good depending on how fast this data is moving. And we saw this initially with our first Schneider case, is that their data kind of looked like this. A moving average of the data kind of looks like this. It's got the right shape, it was just delayed by a few time steps. It took us a long time to debug this to figure out like why it was delayed by more than 2 or 3 time steps. There was an outlier in the beginning of the data set that had forced the rest of the data to all be in a single bucket. So the moving average helps in some cases because we were making kind of very inaccurate predictions, but kind of still got closer values, but it can also kind of hide some of these issues because even if you predict the wrong bucket, or you don't have to be using a full resolution, one bucket can make a certain amount of prediction by itself. So yeah, this is the CLA, and it's conceptual and practical glory.
Yeah, so can some of those similar conditions be like an alert? Be an alert to, like for example, you see a swing like of the max.
So in general,
so it became a hint for us to debug or something like that.
Right. Yeah. So in general, right now we're not very happy with our adaptive encoder approach. It was just something to get the product out the door. So it's saying if we don't know what to do, this is what we can do. It was really never meant to be a permanent solution because of all these issues. It's something that we want to work on. It's in like the big backlog of all these problems that we have that need to work on. So the general policy right now is for all our data sets, do some pre-processing and pick a reasonable min and max. Just avoid this issue. Because in the
that is a like our personal our people would do.
Yeah.
I see.
Yeah.
The cleansing of the data.
Yeah. Yeah. You don't have to change the data, but just when you in Grok, if you specify a min and max, like if you say the min is 0 to 200, then it will use a non-adapting encoder, which means anything beyond 200 will just get clipped to 200. It'll get the same representation. So it avoids that issue at least. The problem is if you pick a very low max, then what you'll see is that everything just gets put in that bucket because everything's getting clipped. But so in general, we just have to say, for our customer proof of concepts right now, pick a reasonable min and max. Anything else?
Okay.
Yeah.
So you convert all those initial dictionary into variables, bit array. But
Right.
then how do you decide the size of this array?
Oh, so for each one of these variables, we binarize it like this into either the category one or the scalar one.
And then
We concatenate them. We
Concatenate.
just concatenate them. So this is just the size is just the sum of all the ends here.
No extra encoding. It's just,
Huh?
there's no extra encoding, just concatenate.
No, there's no extra encoding beyond that. The spatial pooler is like the next level of encoding in the sense that it tries to pool those similar things together. Okay. All right. Well, thank you guys for your time. Hopefully you and TV Land found this helpful.
Great. Thanks.
Thank you.